This lecture is about sound. At the very end of the lecture, you will see the wave equation once again. Now, the derivation is going to be long. It'll involve new concepts. But I want you to reflect upon one thing. Earlier on, when we studied the simple harmonic oscillator, we saw that you release a mass, it vibrates. Okay, the simple harmonic oscillator then occurs again and again in physics. It's the pendulum, it's the spring and mass. It's also the inductor and the capacitor. And it comes again and again. But now we're going to be talking about sound. And sound is going to give us a wave equation. And the wave equation is about oscillations. And the oscillation is almost always about the simple harmonic oscillator. But where is the simple harmonic oscillator here? Where is the mass and the spring? So that is really the beauty of physics. That very, very different situations lead to the same equations. And those equations are correct because you can test them out. So here, as we begin, remember that sound travels in air, also in water, also in other places, but we're going to be talking about sound in gases. And gases are lots of atoms or molecules that are moving around randomly. And so the mystery is, where is the simple harmonic oscillator in a gas? We'll understand this point as we go along. Let me begin by giving you a qualitative understanding of the nature of sound. So take this animation here, produced by the University of Colorado. Let me begin by asking it to put out sound waves. So this loudspeaker here has a diaphragm which is going back and forth, and it is pushing the air sometimes forward and sometimes pulling it inwards. And in this way, what we have are sound waves traveling outwards at some speed, which we will be able to calculate by the end of this lecture. I can ask it to play a tone. So if you hear it, this is what it sounds like. Now I can either decrease the frequency or increase. I can change the amplitude. The amplitude can become so small that at the end there's nothing. I can also, instead of asking it to put out a continuous wave, put out a pulse. So let me put out a pulse here with some reasonable amplitude, and let's see what that looks like. So this pulse has gone out and it's spreading and spreading. And as it goes out, this circular wave or spherical wave becomes flatter and flatter until it becomes a plane wave. So you see the wave front here becomes flatter and flatter, and it becomes a plane wave very far from the source. Okay, now let me ask it to play continuously. But now I want to show something else. I want you to see the graph of pressure along this line, along this dotted line over here. And you see that if you have some means of measuring the pressure, that this pressure is actually at each point. So let's fix our attention at position 450 centimeters from the source. Okay, so here the pressure is sometimes increasing, sometimes decreasing, and is sinusoidal. So if I was to put out a pulse instead, watch what would happen. You see that a pulse will travel through, it'll reach this point at 450, and then it'll exit. it'll be lost, it'll dissipate itself. Now, what's happening to the molecules of the air or the atoms in the gas? There's no sound. I'll turn it on later. But you see that each atom is jiggling about. Why? That's because it is experiencing collisions, forces from its nearest neighbors. And so it is performing actually a random motion. On the average, it's pretty much staying where it is. It's staying close to its average. So there's no movement either to the left or right or up or down or in or out. The average position remains fixed. However, about the average, there will be fluctuations. Now, there'll be more fluctuations if the temperature is higher, because higher temperatures mean more collisions with neighbors in a certain amount of time, and so the motion would, the random motion would increase with temperature. Now let's put out a pulse and see what happens. Let's put out a wave and let's see what both of them do when there is a sound wave. So I'm going to turn the sound wave on. And you see that the average particle doesn't move. The average position of the particle remains fixed. The pressure of the gas is increasing, decreasing, increasing, decreasing. And now that is what we will be using in our analysis of sound. Since we know that sound is pressure fluctuations, let's discuss briefly pressure fluctuations in a gas. In a gas. Now, suppose that this is a certain volume of space, and I will always take this to be an area. So it's properly, I should draw it like this, that this is an area and this is an area also. So this is unit area here, unit area here. The loudspeaker is over here to the left. And this is some volume of space. And now it'll be easier for me if I, instead of drawing this three-dimensionally, I just draw this here as a line and this here as a line. Now, the pressure at any point, so if this is the x direction, the pressure is a function of where you are and the time, because obviously with time the pressure here will change and the pressure here will change also, but differently. Now the pressure at any position at any time is the average pressure. So suppose there was no sound. If there was no sound, then this would be just a constant, just the normal atmospheric pressure P0, which doesn't depend upon where you are and at what time. And then a component that will be the fluctuating part. And this P will be a function of x and time. And this is the fluctuation. Now, the atoms in this, of course, are affected by the sound wave which comes from the left. And so each one of these is displaced by some amount, and this then goes into a larger or a smaller volume, a different volume in general, with the same number of particles. So you could say that all the atoms along here have moved on the average to here, and those are over here have moved here. Well, the volume has changed. So the volume has also changed a little bit, V0 plus delta V. And of course, the density has changed as well. So density, which is the number of particles per unit volume over V, that also has a steady component and a fluctuating component. So this rho zero is independent of where you are. It's the normal density of air, and it doesn't depend upon space or time, but this does. So it's different at different positions at different times. We define something called the dilatation as follows. Dilatation is defined as delta V divided by V naught. So if V naught is the volume here of the volume occupied by these particles, then it changes slightly when the pressure wave comes, and this ratio delta V over V naught is what we will call delta V. Similarly, we'll define the density fluctuation as follows. It's delta rho over rho naught. So this delta rho is actually the same as this. So delta rho over rho naught. This is what we will call delta rho. Now, the number of particles doesn't change, and so rho naught into V naught, that was the number of particles before the sound wave hit it. So the density of number of particles per unit volume multiplied by the volume was V naught over here, and now that has to be the same as rho into V, and that means that this is equal to rho naught plus delta rho into V naught plus delta V. So this delta V is the same here as here. And this is rho naught V naught plus delta rho V naught plus rho naught delta V, and then delta rho into delta V. Now, this is very small, so is this very small, so we are multiplying two very small numbers together, and so we ignore this and put it equal to 0. And so from here, we see that rho naught V naught is equal to rho naught V naught plus this, which means that this here has to equal to 0. And so let's write that out. That's delta rho V naught plus rho naught delta V equals 0. And now divide by V naught delta naught. And so this tells us that delta rho over rho naught is equal to minus delta V over V naught. In other words, what we've shown is that delta rho is the same as minus delta V. So the dilatation and density fluctuation are the negatives of each other. So that means, of course, that this is simply telling you this, that when the volume changes, well, the density will change as well, and the number of particles has to be conserved, and therefore this relation over here must hold. Now let's come to another issue, which is the compressibility. If you have a certain volume, so the particles in here now obviously, when you squeeze it and the volume decreases, you've got to apply some pressure. So when you apply a pressure so that this gets squeezed, then and only then the volume will decrease. Now, some materials or some gases are softer than others and some are harder. We define what is called the bulk modulus as follows. It is defined as minus the difference of pressures that you must apply divided by the fractional change of volume. So delta V over V. What this means is that you must apply a pressure. Look at it this way. The change in pressure that is needed, so if you write it this way, maybe it's more understandable. Delta P is equal to minus, let's give this a name, B as the bulk modulus. So delta P is equal to minus B into delta V over V. So that says that if you apply a pressure delta P, the volume will decrease. That's why there's this minus sign over here, and it'll decrease more if B is small. And conversely, if B is very large, then the change in volume will be very small for the same difference in pressures. Now, this bulk modulus is going to be very important when we discuss sound propagation. And we need to know now what it is for a gas. Let's work out the bulk modulus for a gas. So we need for this the equation of state. Equation of state means, it's also called EOS, equation of state. Equation of state means that you know the pressure as a function of volume. And if you know this, well, then from here you can calculate B, which is, as we just discussed, is defined as minus delta P over the fractional change in the volume. So it's best to write this as a derivative. So it's minus V dP by dV. Let's now see what are the possible equations of state for a gas. Okay, so there are two possibilities. And let me draw a cylinder here. And this is, let's say, a piston with which you apply a pressure P. There are atoms in here moving around. And then let's take the first case, which will be isothermal, meaning the following. I keep this at fixed temperature. Fixed temperature T. Now, you know from your earlier studies that in that case, the product of pressure into volume, so V is the volume occupied by the gas, P is the pressure that you've put on this externally. Pressure into volume is equal to a constant. And in fact, you know what that constant is. It's the number of particles times Boltzmann constant times the temperature, but we're not going to use this. So it's just that pressure into volume is equal to constant. And that's, of course, what is known as Boyle's law. P is proportional to 1 over V, etc. So in the isothermal case, what you do is you apply a pressure keeping the temperature of the vessel constant. Of course, this means that you've done work on the gas, and so you've put in energy. To keep it at fixed temperature, you must convey heat away from the sides. The other situation can be that you don't allow the gas inside over here to communicate energy with the outside, and so you're applying a pressure. There is no way that energy can be released from the sides, and in this case, PV to the gamma, where gamma is a certain constant, which I'll tell you, this is a constant. And here, gamma is the ratio of two quantities, Cp by Cv, which is 5/3 for single atoms. Now, don't worry about this if you don't know it. If you learn this in a thermodynamics or statistical mechanics course, but there's no way that we can get away without talking about the equation of state. Now, from here, we can calculate B. So B for in the first case, let's see what it is. It is minus V d by dV of P. And P is equal to a constant. This constant over here divided by V. And now when we differentiate, d by dV of V will get minus 1 over V squared. So that gives you the same constant divided by V. But we see that that's just equal to the pressure from here. From here you can see that the pressure is constant divided by V. So this is for isothermal. What about this case? Well, we'll do exactly the same thing. We'll take minus V d by dV of constant, some other constant, doesn't have to be the same, divided by V to the gamma. And now this here will give gamma V into C over V to the gamma. And now this over here, this V, one of these cancel, and so this is equal to just gamma times P. So the difference between the isothermal and the adiabatic is that here you have P, here you have gamma times P. So the question is, which holds for sound in a gas? And the answer is adiabatic is more correct, is closer to the observed. And let's reflect a little bit upon that. What this is saying is that suppose a pressure wave comes and there's some small volume over here which then expands and or contracts and becomes bigger like this. Well, on the average, these molecules do not lose energy. So it is an adiabatic compression or expansion. And so therefore, the equation of state that we should use for sound is actually this over here. Let me now derive the wave equation for sound. And this will be done in several stages. So first, let's take equilibrium. In equilibrium, there's a certain volume that I'm going to look at, a small volume. Let's call it volume number 1. And the speaker is to the left. So the speaker is somewhere over here. Let's call this the position x, this the position x plus delta x. In equilibrium, which means no speaker sound, we'll have simply that P of x is P of x plus delta x. So the pressure here and the pressure here are exactly equal. And so if there was no sound, well, nothing would happen. The molecules would be moving around randomly over here, but on the average, there'd be no motion of there'd be no average motion of these atoms or molecules. But now suppose we turn the speaker on. Okay, then these atoms, the atoms which are close to this position over here, will move somewhere here like this. So let me draw that in this way. And the atoms that are close to this will move here. And let me draw that here. Now I'm going to call this the distance x plus epsilon, and this epsilon will be a quantity that depends upon both position and time, but I'm not drawing time, I'm not indicating time here explicitly. And similarly, this is going to move here, and this is going to be the position x plus delta x plus epsilon. Now epsilon is a function of x, and this is a different x, it's x plus delta x. So the earlier separation, the separation earlier was between here and here, and that was equal to delta x. The separation later well, see what that is. That's this position minus this position. So, yes. That's this position minus this position. So that's delta x plus epsilon of x plus delta x minus epsilon of x, and that is delta x. Now you see, this difference over here is just d by dx delta x. As I said, this epsilon, which is the displacement from the average, is a function of x. Okay, so now when I turn the speaker on, this disturbs the equilibrium. That means that the pressure here and the pressure here are not going to be equal to each other. So let's remember what we had just learned, that when you squeeze something, then delta P is minus B over V delta VA. That I'm taking this to be the position A, so let me call it. So at this position A, let's call this XA, this position here XB. That's so that I don't have to write XA is equal to X plus epsilon and XB is equal to all of this. So the extra pressure, the fluctuation pressure, which comes from changing the volume a little bit. See, this is going back and forth like this. That is equal to minus B. Now, the volume, this volume is only slightly different from this volume. And this volume over here will be the cross-sectional area A. So this can be assumed to be either a unit cross-section or a cross-section A multiplied by the distance. So think of this as two plates of area A separated by distance delta x. So the volume is A delta x. And of course, this will be very close to that, although not exactly. Now, delta V is just A delta epsilon. So what that is saying is that there'll be a small change of volume because epsilon has changed slightly, and this is equal to minus B dE by dx at x equal to xa. Similarly, delta PB will be equal to minus B delta E by delta x at x equal to xb. It's very important to realize that the excess pressure here and the excess pressure here will not be equal to each other. And pressure depends upon where you are in the gas. Now, here's an obvious fact that all the molecules in here and all the molecules in here, if we add up the number of molecules in here and the number over here, their numbers will be equal, and so therefore their masses will also be equal. So if we call this section 2, the mass of section 1 is obviously equal to the mass of section 2. And it's easier to take the first. Let's do that. This is the equilibrium density rho naught times the area times the separation delta x. So this is the volume A delta x multiplied by the density, and that's the mass over here. Now, let's apply Newton's laws, Newton's second law of motion, which says that the mass into acceleration is equal to the total force that is acting on the body. Now let's ask what we mean here by mass, acceleration, and force. The mass is the mass of the atoms which are contained inside either this or this. They're both equal. And so the mass is this. Acceleration. Acceleration of what? It's epsilon that is actually changing with time. So it is the acceleration of the position of these atoms. So mass into acceleration is equal to the net force. Now let's calculate the net force. Force is area into pressure. So A into the pressure here minus the pressure, A into the pressure here. So it's A into the pressure at x equal to A minus A into the pressure at x equal to B, x equal to xb. So that will be the net force that is acting upon the atoms contained here. And now we know how to work this out, because the pressure at x equal to xa is simply this. It is minus B. So this is A, and this B over here will come here. So this is minus AB dE by dx at x equal to xa, and minus, and there are two minuses, so that will give you a plus. So plus AB dE by dx at x equal to xb. And so from here, let's divide both sides by AB. In that case, we'll have rho 0 over B d2 epsilon by dt squared equals d epsilon by dx at x equal to xb minus d epsilon by dx at x equal to xa divided by delta x. So this delta x I've brought down over here, but then you recognize that the difference of two first derivatives at slightly different points, this is just equal to the second derivative of epsilon. And so finally we have got the wave equation, which says d2 epsilon dx squared equals minus, well, is equal to plus rho 0 over B d2 epsilon dt squared. And that's obviously saying that this is of the same form as 1 over V squared d2 epsilon by dt squared, provided that the speed of sound squared is equal to B over rho naught. And that is the velocity of sound. It's so the bulk modulus divided by the density, the equilibrium density of the gas. And that's a very important result. Now, what does this have to do with a harmonic oscillator? Well, the point is that you have a restoring force when the gas is disturbed from equilibrium. And that restoring force is increasing as the distance. So it's increasing as epsilon itself. And so this has given us a very important result, that if there is more bulk modulus, that is to say, if there's greater resistance offered by the gas, that is, if it is stiffer, then there will be a higher velocity of propagation of the pressure wave. It also is telling us that if there is more mass per unit volume, the speed will be slower. And this makes a lot of sense because, of course, if you have more mass, then you have more density in a given volume, and hence to move that will need greater force, and hence the velocity becomes slower. Now notice finally that we have used, in deriving this wave equation, the assumption that epsilon is small. And so this is for small amplitude oscillations only. So this is limited to small oscillations. What happens when you have large oscillations? When the pressure changes hugely, then you can have what is called a shock wave. Okay, that's all for now.